while talking of the Poisson process, I said we have to first talk about a counting process, and so we said that there should be some norms for the have to be followed for the counting process. And so, the first one is that it should have independent increments. I should underline independent increments. Okay. So, that means that the number of events that occur in disjoint intervals are independent. So, that means, say for example, if you are saying that up to 8 a.m. you are counting the time, then n8 would be the number of events that have occurred up to time 8, and so that n8 will be independent of, say for example, the number of events that have occurred in the from between at 8 and 10 a.m. So, that means n10 minus n8. So, both these are random variables, and so we will assume, because the intervals are disjoint, this is up to 8, let us say 0 to 8, and then this is from 8 to 10. So, the two intervals are disjoint, and therefore, we expect we want that these two the number of events, that means the corresponding random variables must be independent. Okay. Now, for the for example, A, that I gave you 3 examples of counting processes. First one was arrivals at a post office, and so example A, this may be a reasonable assumption, because we may assume that people, as long as for the time that the post office is open, people will come in any time, and so people coming, say between say up to from if it is open from 8 a.m. then 8 a.m. to 10 a.m. the number of arrivals, and the random variable indicating the number of arrivals, and say between 10 and 12 the random variables, 2 random variables giving you the number of arrivals in these disjoint intervals are independent. Okay. Now, for B, which is the number of births in a particular town, or this number of births between time t and t plus delta t, suppose we are taking, will be large if n t is large. So, that means that if you are taking it over a long span, then at a particular time when the population is large, then the number of births will be large. So, here it will depend, that means it does not seem reasonable that n t is independent of n t plus delta t minus n t for any t. So, it will depend, see this will depend on the number of births that occur if you are taking up to, or in the sense that we are saying that the random variable n t and the random variable n t plus delta t minus n t may not be independent if you are. Okay. Now, for example C, it will be a reasonable assumption. So, this example C referred to the number of goals that are hit by a hockey player. So, here again if you take the time span to be one season of hockey tournaments. So, during one particular season, we expect the hockey player to be either to have continue to have a good form or not have a good form. So, if he has a good form, then he will hit a number of goals hit by him up to time t, or from t to s plus t should be the 2 random variables should be independent. Okay. So, the time span is important, right. If I take the time span to be 2 years, then certainly it will matter, because one cannot maintain a form for, let us say, up to 2 years or 5 years. So, the time span. So, if you restrict your time span, then C would be a reasonable assumption. For C, the independent increment assumption would be reasonable. The other important assumption for counting process is stationary increments. Right. Now, here what we are saying is that the number of increments that occur should depend only on the length of the interval. So, here for example, if you have s comma s plus t, then the length of the interval is t. So, it will not matter what value s takes, as long as the interval length has time t, then the number of increments that occur during this interval is just dependent on the length of the interval, right. Now, here we can again see whether the counting processes that we wrote down is that a reasonable assumption for all those counting processes. For example, for A, it is not a reasonable assumption. Why? Because for a post office, and even so similarly you can consider a bank, there may be a rush hour. If there is a rush hour, then certainly you can't say that this and this are independent. Say if that this is the rush hour, then you know that there will be more arrivals, and so the random variables n8 and n10 minus n8 would not be independent. Okay. So, if you have the concept of a rush hour, but if you sort of ignore the rush hour and then you look at the counting process for a post office, then this may be assumption of stationary increments may be a reasonable assumption. Now, again for B, it may not be a reasonable assumption. In this case, some sort of pattern has been observed in the number of births. See, summer time more babies may be born than during winters, and so again if there some pattern has been observed in the town that you are considering, then again B may not be, because it will not follow the assumption of stationary increments. Okay. So, it will matter if your time span is during summer. So, then for the same period more babies may be born as opposed to the time span if this is during winters. Okay. So, for the same length of time the two may not be the number of events in the interval has the same distribution for all S. So, it may be different distributions. Okay. Then again for C, it will be reasonable. Here again, if we are saying that if the person, if the player, if the hockey player is in form, then surely the number of goals that he hits will depend on the length of the time that he has played. Okay. And so, it will have the same distribution and will depend on the distribution of the number of goals that he hits would be dependent on the length of the interval and not on the when he hits. If I am again restricting myself to let us say one season or maybe 2 seasons, if that is considered to be reasonable, that a person will continue to be in form for a player will be continue to be in form for 1 season or 2 seasons maybe sometimes. So, it depends whatever the way to look at it. In that case the stationarity increment assumption would be a reasonable one for C. And so, this is what I am trying to say is that you have to before you start applying modeling a situation, for example, a particular counting process, you have to see that certain basic assumptions are satisfied, and in that case you can then we will see that based on these two assumptions we can now talk about the Poisson process. So, these are the two basic assumptions under which we will now formulate our this probabilistic model for the counting process, and which we will define as the Poisson process. So, after having defined a counting process, now I make a definition of a Poisson process. So, what we are saying is that the counting process n t greater than or equal to 0 is said to be a Poisson process if it satisfies the following conditions. So, as we said that we start the counting from time t equal to 0. So, n 0 is 0, then this has independent increments, which we have already said that we defined the conditions for a counting process, and then we said additional properties has independent increments. Then 3 is that number of events that occur in any interval of length t has Poisson distribution. See, this is the thing. So, therefore, we are saying that it will be a Poisson process, the counting process will be a Poisson process if the number of events that occur in any interval of length t has Poisson distribution with mean lambda t, where lambda is some constant, positive constant. So, that means what we are saying is that because the interval of length is t, time interval is of length t. So, therefore, probability of n s plus t minus n s equal to n, because what we are saying is the number of events that occur in this interval s plus t comma s or okay, you can say that the length of the interval is t equal to n will be e raised to minus lambda t raised to n upon n factorial, and n varying from 0. So, this is your probability for any value of n here, integer value of n, right. So, now since we are since this probability is only dependent on the length of the time interval, that is t, it is not dependent on when the counting process is started, the beginning of the interval. So, therefore, you can immediately conclude that the process that we have defined also has the stationary increments property, right, which we said that it does not matter, it is only the number of events that occur will depend on the length of the interval and not on when you started counting. So, therefore, this would be a Poisson process, that is what our definition is. So, now let us just look at this definition and see, you can of course, condition 1 is fine, that simply says that counting begins from time t equal to 0, which we have been saying repeatedly. Then 2 can be verified from the knowledge of the process, that it has independent increments, whether this is a valid assumption or not for the process that you are trying to model, then you can tell from the knowledge of the process itself, right. Now, 3 says that the number of events that occur in any interval of length t has Poisson distribution. So, it is not clear how to verify 3. I mean, this is the whole thing. I mean, if I am calling a process a Poisson process, then I am just saying that the number of events that occur here follows a Poisson distribution. So, it is not clear, and therefore, this definition is not a very implementable decision, or you cannot really verify this condition because right. So, therefore, an alternate definition is needed to determine whether a counting process is a Poisson process or not. We would be wanting to have another definition, which hopefully would be more easily implementable or verifiable, that a given counting process is Poisson or not. So, let us see. So, here we will say that again the same mean lambda t, if it satisfies the following conditions. So, counting process is said to be Poisson with mean lambda t if it satisfies the following conditions. So, this is same as for the first definition, n 0 is 0. Now, what we are saying here is that probability n h equal to 1, that means in the time interval h, your probability that n h is equal to only one arrival takes place or one event occurs, it should be in this form, that means lambda h plus order h. Now, this of course means that your function here is of values of a higher order than h, and you say this is higher order of h. So, this is linear, that means the terms here would be square, cube, powers of h. In other words, you can say that what this means is that limit O h upon h as h goes to 0 is 0. So, therefore, this is of higher order than h, square, cube, this. For example, if you take O h to be h square, then h square upon h, limit of this as h goes to 0 is 0. So, this is the idea, that means higher order terms here. So, this, and so what we are trying to say is that you can always discretize the occurrence of the events. That means, if you make the interval h small enough, then there will be the probability of an occurrence of an event is positive in a small interval. So, therefore, you can discretize and the second one, and of course, okay, this is the third condition. The second of course, is the same as that one, that process has stationary and independent increments. So, these two properties we require for the counting process to be able to say that it is a Poisson process, right. So, this has to be satisfied. Now, this one tells you that the probability of the occurrence of event in a small interval is dependent on lambda, and that you can separate out the. So, in other words, the bunching of occurrences of events is not permitted here. That probability n h greater than or equal to t is of order h. So, that means, when h is small, this probability is really very small of two or more events occurring in a very small interval of time h. So, that is of order h, and since, as I have told you, that this means that the higher powers of h than linear. So, therefore, this would be when h is very small, this will also be very small. So, given lambda positive, the same lambda we are saying here. When I say this, that means it is understood that lambda is greater than 0 here. Right. So, this is the alternate definition, and let us now see that obviously, when we are saying that this also describes a Poisson process, that also describes a Poisson process, there should be, we should be able to show that the two definitions are equivalent, right. So, I will do it both ways. I will first show that definition 1 implies definition 2, and then show you that definition 2 implies definition 1, and this is very interesting and nice, simple. So, here see, we start with this. Definition 1 says that probability n of t plus s minus n s equal to n is e raised to minus lambda t, and lambda t raised to n upon n factorial, and n varies like this, right. Now, put s equal to 0, t equal to h, because this is for all s t, and n equal to 1 in this equation. Then you obtain that probability n h equal to 1, right, because this is 0, t is h, s is 0. So, n h equal to 1 is given by e raised to minus lambda h, then lambda h raised to n is 1, and this is it, right. Now, just expand e raised to minus lambda h, that will be 1 minus lambda h plus lambda h whole square by factorial 2 and so on, multiplied by lambda h. So, when you bring lambda h inside, this will be lambda h plus all terms will be of higher order, because this will be square h square, this will be h cube and so on. So, I can write it this way, right, and which satisfies. So, right. So, that means your condition 3 implies condition 3 here for the definition, the second definition, and similarly it is also implied from here, because when you want to compute this probability n h greater than or equal to 2, this will be 1 minus probability n h equal to 0 minus probability n h equal to 1. So, n h equal to 0, again since your definition is saying that when n is 0, the probability is e raised to minus lambda h, that is all, right, because your n is 0. So, that is e raised to minus lambda h, and this is probability n h equal to 1, we have just computed is this thing. So, minus lambda h, and order minus or plus does not matter, you whatever. And now, you see when you expand this, because this will be 1 minus of 1 minus lambda h plus lambda h whole square by 2 factorial minus lambda h plus O h, right. So, then so you have a minus sign here. So, this becomes plus, right, because minus and then 1 minus lambda h. So, therefore, this is 1 cancels out, lambda h minus lambda h cancels out, and you are left with something, because this is order h. So, order higher than h, and this is also O h. So, therefore, the whole thing is O h, right. So, you can see that definition 1 implies definition 2, and now we will show you that definition 2 implies definition 1, and you will see that this, then we would most of the time be working with this definition of the Poisson process. So, let us see, we will try to now show that definition 2 implies definition 1. And of course, then we will talk about inter-arrival times later, but you see here probability n t plus h. So, this I am saying is the probability of n t plus h is equal to n. This is what we are saying, what we mean by this. So, this is a new notation I have started. So, p n t plus h, that means number of arrivals are n in up to time t plus h. Now, this can be thought of as n minus 1 arrivals up to time t, and then 1 arrival at within the interval h, right. That means, see from t plus up to t plus h, you want n arrivals or n occurrences. So, up to t, if there are n minus 1 occurrences, then in the interval time length of h, you want 1 arrival, and according to our definition 2, this is the probability of one arrival in the time interval h, length of interval is h, right. And since we are talking of independent increments, so this will be product. That means, I can say this plus there is no, that means there are n arrivals up to time t, and there is no arrival in time length h. This is what and this will be probability n h equal to 0, which follows from 3 and 4. See, 3 said that probability of one arrival is 1 is lambda h plus order h, right, and probability n h greater than or equal to 2 was of order h. Right. Now, when you say that there is no arrival, then that means you want 1 minus probability n h, because right, you want this to be. So, if you take the complement, so then n h greater than or equal to 1, would that be okay? See, if you want n h equal to 0 in time, so that means arrivals are 1, 2 and so on in the interval h. So, 1 minus of that will be right. So, therefore, yes. So, this would be then 1 minus lambda h because this is O h and this is lambda h plus O h. So, therefore, this is what you have. So, therefore, probability of n h equal to 0 is 1 minus lambda h minus order h. So, again independence of events, independent increments. So, this will be p n t into this, right. So, this is how you can describe n events in time up to t plus h by breaking up the event into number of arrivals up to time t, and then n minus 1 arrival in time h, or n arrivals up to time t and no arrival in time n h. So, this is how we will write it down, right. And therefore, this will be, if you simplify this expression, p n t is coming from here plus lambda h p n minus 1 t minus p n t, right. So, this is it, plus all terms are of higher order of h, right. Now, just rewrite this. This is p n of t plus h minus p n t divided by h. So, that will become I have divided by h here. So, lambda times p n minus 1 t minus p n t, and this is order h upon h. Now, when you take the limit, you can immediately see that when you take the limit as h goes to 0, this will be limit as h goes to 0 of this, and here this will be lambda, this is independent of h, and this we have seen will go to 0, right. Order higher order of h means that this limit is going to 0, right. So, this is what you have, and then this is nothing but the derivative of p n t. So, this will be the derivative, and this is equal to lambda p n minus 1 t minus p n t. Now, so, this is valid for n varying from 1, because you have this n minus 1, and d p 0 t upon d t is minus lambda p 0 t, because when you are looking at n equal to 0, see from here, then you do not have this, you simply have this, right, p n t, because I should have n equal to 0, and right. So, it will be okay. If you want me to write it down separately, see here becomes crowded. So, this will be p 0 t plus h is p 0 t. So, no arrival up to time t and no arrival in the time interval. So, will be 1 minus lambda h. Remember, I can ignore that term, because that will anyway go to 0. So, then this will be p 0 t plus h minus p 0 t divided by h. So, limit of this as h goes to 0. Okay, it is not legible, but you can I am talking loudly, so you can hear. So, this is equal to p 0 t minus into lambda, right. So, this is therefore, this is derivative d p 0 t upon d t is equal to minus lambda p 0 t, and so you this much knowledge you have about the differential equations. So, here from here it follows that p 0 t is e raised to minus lambda t, and so you have these two sets of differential equations. So, here the solution is immediate, and then this is n from 1 to t. So, if you put like for example, n equal to 1, it will be d p 1 t upon d t, which will be from here minus lambda p 1 t plus lambda e raised to minus lambda t, because I am substituting for p 0 t. See, when n is 1, this is p 0 t, which is e raised to minus lambda t. So, therefore, this is it, right. Now, of course, there are methods to solve these differential equations, not difficult, but what we are saying is that if you just try p 1 t equal to lambda t e raised to minus lambda t, it will satisfy this equation, right. Just differentiate and substitute here, the two sides will be equal. So, P 1 t is a solution here, and then in general the solution would be P n t. You can very easily verify that for all values of n, this is the solution to your general differential equation that you obtained here. And this is nothing but, as I said, that my definition is that P n t is nothing but probability of n t equal to n. So, n arrivals up to time t. So, therefore, you see all other conditions remain the same in the definition 2 and 1. This was the only thing, because we were not sure how we would go about verifying in definition 1 that the number of arrivals in a time interval of length t will follow Poisson distribution. So, now using these properties, a probability of definition of a number of occurrences in the time interval h, given those the third and fourth condition of definition 2 help us to show that the number of probability of number of arrivals up to time t would be follow a Poisson distribution. So, a nice way of showing that, and because therefore, definition 2 is easier to verify. We feel, because that to digitize and so on, you can sort of approximate the condition 3. Actually, that is the important one in definition 2, and then that is probability of one occurrence in time interval length h is of this order, that you can supposedly easily verify, and there are methods to do it. So, therefore, most of the time we would be, but now once we have established the equivalence of definition 1 and 2, it does not matter, whichever you feel when needed, you can use it in your when you are trying to analyze certain results and or obtain certain probabilities. Okay. Now, as I had written there, inter-arrival times, we would now like to look at the probability of that means the time. So, here time between two occurrences, because again the occurrences are all chance events, are unpredictable. So, we want to now look at the, if it is possible to determine the distribution of these inter-arrival times, right. We have seen that probability n t equal to 0 is e raised to minus lambda t. So, no arrival from 0 to time t. This is your. So, that means up to, and if you define x 1 as the time of the first arrival, if the time of the first arrival, and then if I want to compute the probability that x 1 is greater than t, that means that there has been no arrival in the interval 0 to t. So, no arrival from 0 to t is the event that n t is 0. So, the two events are the same. That means, if the first arrival has not occurred, the time for the first arrival, see x 1 is the time of the first arrival. So, if the first arrival time is greater than t, that means in the interval 0 to t, no arrival has taken place, which implies that n t is 0. So, the two events are the same. Okay. It is just that here we have defined the random variable n t, and here is the random variable x 1. So, therefore, and this probability is e raised to minus lambda t. So, if somewhere I have written that this event can be taken as x 1 greater than or equal to t, then this is not correct, because you are saying that the time of the first arrival is greater than t. So, it cannot be, or if you are saying that n t is 0, then this is equivalent to the event that x 1 is greater than t. It cannot be greater than or equal to t, because in the time 0 t, no arrival has taken place. So, any arrival that takes place will be after t. So, this is the important thing, and therefore, 1 minus f of x 1 t. So, this is 1 minus of f x 1 t, if f is the cumulative distribution function for x 1. So, then this is equal to e raised to minus lambda t, and so f x 1 t is 1 minus e raised to minus lambda t. So, this gives you the, and so that shows you that therefore, your f x 1 will be lambda e raised to minus lambda t. So, if you differentiate this equation on both sides, you will get lambda e raised to minus lambda t. Now, this is a exponential lambda. So, the distribution of x 1 is exponential lambda, and therefore, the expectation is expected value of x 1 is 1 upon lambda. So, this tells you what, that 1 upon lambda is the the mean time of first arrival, right. But actually now if you look at x 2 as the elapsed time between the first and the second arrival. Okay, that means here the first arrival occurred here and the second arrival occurred here. So, I am calling this as x 2. So, that means if this is x 1, so the time of the first arrival is x 1, then time of the second arrival will be x 1 plus x 2, because this is inter arrival time. So, x 2 is the time between the first and the second arrival. So, for example, so now if you look at that is why I have defined here, this is the elapsed time between the first and the second arrival, or this occurrence. I keep calling arrival, but which also means the occurrence. Okay. Now, if you want to look at this probability T 2 greater than T, condition that T 1 is S. So, the first arrival took place, we are writing T 2 T 1, but here I have been writing x 1 x 2. So, it does not matter, you can make it x 1 and we can make this as x 2, because this is x 2. Okay. So, x 2. So, therefore, this will be probability n s plus t minus n s is 0, because the second arrival is not has not taken place up to, I mean this length is not is bigger than t. So, therefore, s plus t will be this. So, n s plus t minus n s is 0, given t 1 is s. So, therefore, probability n s plus t minus n s 0 is e raised to minus lambda t. Okay. So, this is again, so you see this will also be 1 minus f x to t, and therefore, you can again see that it will be exponential. So, we will continue with the so that means the inter arrival times are all exponential, and that you can relate it with the memoryless property of the exponential distribution, which comes to your independent increments. So, the two things are related. In this exercise 8, I will be going over some problems related with the limit theorems that we had done, and also the Poisson process that we had talked about after that, right. Okay. So, so x 1 and x 2 are question 1, x 1 and x 2 are independent random variables, x 1 is binomial n I comma p I 1 to 2, right. So, x 1 that means is binomial n 1 comma p, and x 2 is binomial n 2 comma p. So, use MGFs to find the distribution of x 1 minus x 2 plus n 2. Okay. So, here you see all that you have to show is, so basically these two problems are on the MGF of the joint density functions of random variables, and then I had also introduced the concept of MGF for more than one variable. So, now here you see you can rewrite this x 1 minus x 2 plus n 2 as x 1 plus n 2 minus x 2. So, since x 2 is binomial n 2 p, your n 2 minus x 2 will become binomial n 2 1 minus p, right. Is that clear? Because you see when you consider n 2 minus x 2. So, if x 2 has r successes, then n 2 minus x 2 will have n 2 minus r successes. So, it will be so therefore, the for n 2 minus x 2 the successes of x 2 would be failures here, and therefore, your you see the probability for a failure is 1 minus p. So, that is all. So, once you recognize that you can write this as x 1 plus n 2 minus x 2, then n 2 minus x 2 is binomial n 2 and 1 minus p. So, once you know this, then you can immediately and then they will be independent. So, therefore, because x 1 and x 2 are independent. So, x 1 and n 2 minus x 2 are independent, and therefore, you can write down the joint MGF. So, you should be able to do it, right. Now, question 2, x 1 and x 2 form a bivariate normal random variable. I mean they are bivariate random normal variables with parameters mu 1, mu 2, sigma 1 square, sigma 2 square, and rho. So, rho is your correlation coefficient. Show using MGFs that y and z given by, so y is defined as x 1 minus mu 1 and z is defined as x minus mu 2 minus rho into sigma 2 upon sigma 1 into x 1 minus mu 1. So, you have to show that these two random variables are independent, and that y and z are each normal random variables. Okay, here the idea is to use MGFs, but actually there is a easier way, and surely to be able to do this problem using the MGFs, I leave it as a challenge, and maybe when I am discussing set of miscellaneous examples, we will revisit this, but right now the way to do it is, see, because y is x 1 minus mu 1. So, this will continue to be normal, remember, because x 1 minus mu 1, the mean of y will be 0, variance will be the same, because by shifting the mean of a random variable, the variance does not change. So, therefore, y is again normal with mean 0 and variance sigma 1, and similarly z is also, this should be x 2 here. That is missing. So, x 2 minus mu 2. So, here again you have shifted the mean of x 2 by this quantity mu 2 plus rho into sigma 2, and of course, this is the whole idea when you write z like this. So, x 1 minus mu 1 upon sigma 1, okay, that is the, because you are computing the, so this is the whole idea. So, here again the mean has been shifted, and therefore, z is also normal with the same variance sigma 2, and the mean would be well. So, by definition of z, we see that z is the random variable which is given by conditioning x 2 on x 1, and we had, while computing the conditional PDFs, we had seen that this will also turn out to be a normally distributed random variable, and you can immediately see that the mean of z, that is the expected value of z, is 0, because expected value of x 2 is mu 2 and expected value of x 1 is mu 1. So, when you take the expected value of z, it will turn out to be 0, right. So, therefore, we need to compute the variance, and the variance will simply be expectation of z square. So, which I have done here by writing out the expectation of the square term, and then taking expectation inside, as we can do it, and therefore, it will turn out to be 1 minus rho square upon sigma 2 square. So, this is the variance. Now, when we want to define the covariance, then it will be y comma covariance of y comma z. So, that will be expectation of x 1 minus mu 1 into x 2 minus mu 2 minus rho sigma 2 upon sigma 1 into x 1 minus mu 1, right. And again here we can take expectation inside. So, this will be expectation of x 1 minus mu 1 into x 2 minus mu 2, and then minus rho sigma 2 upon sigma 1 expectation of x 1 minus mu 1 whole square, and expectation x 1 minus mu 1 into x 2 minus mu 2 is the correlation coefficient rho into sigma 2 sigma 1, right, because expectation of x 1 minus mu 1 into x 2 minus mu 2 is the covariance, and so that can be written as rho into sigma 2 sigma 1, then minus rho sigma 2 upon sigma 1 into the expectation of x 1 minus mu 1 whole square is sigma 1 square. So, therefore, when you substitute that value, you turns out to be 0. So, y and z are uncorrelated, and now we use a result that for if y and z are normally distributed, then being uncorrelated is equivalent to their being independent. So, therefore, y and z are independent, right. Okay. Question 3 is from an urn containing 10 identical balls numbered 0, 1 to 9, n balls are drawn with replacement. So, we draw a ball and then put it back. We just notice the number. In the following, let occurrence of 0 on a draw mean that the draw yields a ball with number 0. Okay. So, a draw, whenever the occurrence of 0 means that you draw a ball, you notice the number or you note it down somewhere. So, if it is a 0, then it is a draw, means that the draw yields a ball with number 0, and then we put the ball back, right. Now, what does the weak law of large numbers assert about the occurrence of zeros in n drawings? So, the mean is 1 by 10, because they are identical balls. So, probability of drawing any ball is equally likely with any of the numbers, 10 numbers is equally likely, and therefore, the weak law of large numbers will say that if Sn is the number, see, we are denoting by Sn the number that number of balls that showed up with number 0. right. So, then Sn by n is the relative frequency. So, out of the n draws you have Sn balls have shown up with number 0. So, Sn by n as n goes as becomes large will converge to 0 in probability, will converge to 1 by 10. The mean is 1 by 10. So, will converge to 1 by 10 in probability, that is your weak law of large numbers. Okay. So, Sn by n will converge to 1 by 10 in probability. Now, B part is how many drawings must be made in order that with probability at least 0.95 the relative frequency of occurrence of zeros will be between 0.09 and 0.11. Okay. So, that means you are wanting to know. So, Sn by n is the relative frequency, you want to compute this probability that the relative frequency is between 0.09 and 0.11, and this probability should be at least 0.95, right. So, therefore, now again I standardize the whole thing. So, this is Sn by n minus 0.1, right. 0.1 is the expected value here, and so subtract 0.1 from either side, and so this finally, because the difference is 0.01. So, this is what you have. Now, by Chebyshev's inequality, this number, this probability is greater than or equal to 1 minus variance of this Sn by n, which is, because this is now binomial. So, 1 by 10 into 9 by 10. So, 0 and non-zero, that is how I am treating this is. So, PQ into 1 by n, because Sn by n, the variance, right. So, variance of Sn is npq and that divided by n square. So, this is 1 by n, right, and so this into divided by, so Chebyshev's inequality 0.01. So, therefore, we will compute the value of n when this is equal to 0.95, and for higher values of n it will be higher, right. So, therefore, now you have the equality, you can now get an equation for n and you will get the value of n, for which this probability would be between 0.019 and 0.11. So, you can do the rest of the problem. Okay. Then part C is use the central limit theorem to find the probability that among n numbers thus chosen 0 will appear between n minus 3 root n by 10 and n plus 3 root n by 10, right. So, here again you want this probability using central limit theorem, right, n minus 3 root n by 10 less than Sn less than n plus 3 root n by 10. So, then you see n by 10 is the mean of Sn. So, I write it here this, and then you see the variance of Sn will be n into 1 by 10 into 9 by 10, right, because Sn is now binomial with mean 1 by 10 and sorry, mean n by 10 and variance npq, right. So, this is this, and so under root of this will be 3 root n by 10. So, 3 root n by 10. So, when you divide, so now this becomes a standard normal variate, and so the central limit theorem says that probability this less than or equal to, I mean for n large enough, less than or equal to 1, you want to compute so this is approximate probability, which is 251 minus 1, right. So, 51 the value is given to you at the end of the problem, and so you can compute this. So, this was a good use of central limit theorem. Okay. Yeah. So, now let us go to problem 4. Yeah, an employee in a call center works from 8 a.m. until 5 p.m. with breaks between 10:30 to 10:45, then from 12:30 to 11:30 and 14.45 to 15 hours. Assume that calls come in according to a Poisson process with expected number of calls per hour equal to 6. So, your lambda is the probability that there are at most 10 calls during the breaks. So, here the whole idea is, because you see it does not matter for the when the arrivals, when the phone calls are coming by as a Poisson process, then the inter arrival times between the phone calls is exponential, which is memoryless. So, that is what you are using here. So, then what we can do is we can just add up the total the break time, which is 15, 1 hour and 15. So, 1 hour 30 minutes, right. So, therefore, 3 by 2 hours, and you want 10, you want at most 10 calls during this 3 by 2 hours. So, therefore, you will have to write the probability. So, you sum up, that means the calls can be 0, 1, 2 up to 10. So, your lambda is 6 into 3 by 2, okay, 6 into 3 by 2, because 3 by 2 hours. So, lambda t lambda t becomes your parameter now, and within this time within the time 3 by 2 hours you want at most 10 calls. So, you can write down the Poisson probability. What is the probability that first call of the day is after 8:10 a.m. So, that means for 10 minutes you do not want any call. So, 0 call, and therefore, again this will be. So, your time would be, you have to see, since your arrival rate is given per hour. So, you have to convert the 10 minutes to the to fraction of an hour, which is 1 by 6. So, therefore, it will be e raised to minus lambda t, probability that no call comes during the time 8 to 8:10 a.m. So, that means 1 by 10 1 by 6 into 6, which becomes, so e raised to minus 1 will be the probability, right. Actually, okay, my idea is not to really give you all the answers, but just to give you hints. What is the probability that the employee can do something else for 45 minutes without being disturbed by a call? So, here again we are repeatedly using the memoryless property. So, 45 minutes can be anywhere, and therefore, you want the break, that means now your time is 3 by 4 hour. So, you do not want any call to come in between for 3 by 4 hours, and your lambda is 6. Okay. Fine. So, you can do this now. Now, consider a Poisson process with parameter lambda. What is the conditional probability that n 1 is n given that n 3 is n? So, here again this is a good question in the sense that it will again help you to understand the Poisson processes. Do you understand why this probability does not depend on lambda, right? So, now here you see what is it that you have to find. You have to find probability n 1 is n given that n 3 is n. Okay. So, which means that probability n 1 is n, and see, actually you can interpret this as know that n 1 is n and then n 2 is 0. Yeah, because n 1 is n and n 3 is also n. So, that means for 2 prime periods 3 minus 1 there has been no arrival, right. So, therefore, this is this, and then divided by probability n 3 equal to n. This is what you have, right. Okay. And so, and you are given so your arrival rate is lambda, right. So, therefore, you have to write this, right. So, n 1 is the number of arrivals, so which is equal to n in time 1 period, and in time 3 period also you are given that n arrivals are there. So, that means all the n arrivals have taken place between 0 and 1, and so there are no arrivals in the time 2 units of time 0, right. And now, if you write out this these probabilities, you see that the answer will be independent of lambda, and again I want you to work out the details. Okay. Then yeah, so question 5 is over. Question 6, the jobs to be performed on a particular machine arrive according to a Poisson input process with a mean rate of 2 per hour. Suppose that the machine breaks down and will require 1 hour to be repaired. What is the probability that the number of new jobs that will arrive during this time is 0, 2. So, that means essentially you are asking for 1 hour gap, that means since the machine is takes 1 hour to be repaired. So, then in this 1 hour you want to know the probability of 0 arrival, 2 arrival or 5 arrivals, and this is the Poisson process, and the mean rate is so lambda is the mean rate is lambda, which is equal to 2, right, 2 per hour. So, this you can say is a simple problem, but again I just want you to familiarize yourself with all these concepts, and therefore, I have done it. Yeah. Okay. Now, question 7, suppose you arrive at a single teller bank to find 4 other customers in the bank, one being served and the other 4 waiting in line. Okay. The statement is a little this thing, because here it should have said 5 people, but anyway 4 refers to the 4 people waiting in the queue, one is being served and you join the end of the line. So, you are the 6th person. So, if the service times are all exponential with rate mu, what is the expected time you will spend in the bank? So, therefore, you see this is 6 service times, because 5 are already there, and because of the memoryless property, the person who is being served, again the probability of its completing, so whatever service time is over is immaterial, right. So, therefore, 6 services have to be completed, and therefore, the completion time for the 6th person is a gamma distribution with mean 6 mu. Or okay, it will be 6 comma mu, right. Yeah, it will be gamma 6 comma mu, sorry. So, it will be 6 comma mu, and therefore, the what is the mean? The mean would be 6 by mu. I think the mean should be n by mu, right, if it is gamma n comma mu. Anyway, just verify that. So, you will find out the expected waiting time of the 6th person when he joins the queue in the bank. Okay. Oh, there should have been a then this 8th one. Okay. So, cars pass a certain street location according to a Poisson process with rate lambda. Okay. So, certain location on the street, the cars are passing at the rate of lambda, and a woman who wants to cross the street at that location waits until she can see that no cars will come by in the next t time units. Right. Okay, she has some idea that she is standing at this particular place, and then she looks at the side and sees that for quite a distance she cannot see any car coming, then she will feel free to cross the street, right, and that time according to her is t time units, something like that. So, find the probability that her waiting time is 0. So, waiting time is 0 means that means she comes to the location, and then the probability that there is no car coming for the next t units, right. So, here again because your arrival rate is Poisson with rate lambda. So, your inter arrival times are also exponential with parameter lambda, and therefore, you can find out the probability that her waiting time is 0. That means, no arrival in the time in a time 0 to t. So, find out the Poisson probability that which is e raised to minus lambda capital T, right, no arrivals, and find her expected waiting time. So, now you have this distribution e raised to minus lambda t as the probability that her waiting time is 0. So, you find out her expected waiting time. So, this you can now do by yourself. To answer the second part, that is what is the expected waiting time of the woman who waits at the crossing for the cars to come. So, you will have to break up the you will have to compute the expected value of the waiting time by using conditional probabilities. So, I will just write down the solution for you on the board. Okay. So, I hope with all these hints and almost some of the problems I have solved almost completely. So, anyway, I hope you will enjoy doing it, and I definitely will try to come up with a large list of interesting and challenging problems at the end of the course.